Have you ever wondered why metals conduct electricity and non-metals don't? Isn't it interesting how these two distinctive categories of elements exhibit such contrasting properties? In our daily lives, we're surrounded by an array of metals and non-metals, each with its unique characteristics. Metals, with their shiny luster, are often associated with strength and durability, while non-metals, varied in appearance, are generally known for their role in the chemical reactions that sustain life. But there's more to metals and non-metals than meets the eye. Beneath the surface, these elements harbor complexities and subtleties that go beyond the common perceptions. They interact, they transform, and they play pivotal roles in the world around us. So what makes metals, well, metallic? And why do non-metals behave the way they do? What happens when metals and non-metals meet? These are just a few of the intriguing questions we'll be exploring. Stay tuned as we unravel the fascinating world of metals and non-metals. So, what exactly are metals? How do we define them? Metals, in essence, are elements that are shiny, malleable, ductile, and good conductors of heat and electricity. They're the stuff of jewelry, coins, and automobile bodies, not to mention the backbone of many a skyscraper. Their common properties derive from their atomic structure. In a nutshell, metals have a sea of free-moving electrons swimming around their atomic cores. Picture it as a busy dance floor, where electrons are the dancers, moving freely and swiftly. This sea of electrons is what gives metals their signature characteristics. For instance, their shiny appearance or luster is due to these free electrons, which reflect light off the surface. Ever wondered why metals like gold and silver are so irresistible to the eye? Now you know. Their malleability, or ability to be hammered into thin sheets, and ductility, or ability to be drawn into thin wires, are also thanks to these electrons. They allow the atoms to slide past each other without breaking their bond. That's why you can bend a metal spoon or stretch a gold chain without it snapping. And let's not forget, metals are renowned conductors of heat and electricity. That's why your stainless steel pot heats up quickly on the stove, and why electrical wires are often made of copper. Again, it's those free-moving electrons at work, swiftly carrying heat or electrical charge from one end of the metal to the other. Examples of metals in our everyday life abound. There's iron in our buildings and vehicles, aluminum in our soda cans, copper in our electrical wires, and gold and silver in our jewelry. And that's just scratching the surface. In the grand scheme of things, metals are the workhorses of the material world, shaping our lives in countless ways, from the mundane to the extraordinary. Their unique properties stemming from their atomic structure make them indispensable in a myriad of applications. That's a brief overview of metals. Now let's delve into the world of non-metals. Non-metals, they're not just the opposite of metals, are they? Let's delve into the fascinating world of non-metals. Unlike metals, non-metals are elements that don't conduct heat or electricity well and are not malleable or ductile. They don't have the shine or luster that we associate with metals. The majority of non-metals are gases at room temperature, with a few exceptions such as carbon, sulfur, and iodine, which are solid, and bromine, which is liquid. Non-metals exhibit a slew of distinct properties due to their unique atomic structure. For instance, they typically have higher ionization energies and electronegativities, which simply means they tend to hold onto their electrons very tightly and are often more willing to gain electrons than lose them. This electron holding capacity contributes to one of the most interesting properties of nonmetals: their ability to form a wide variety of compounds. Carbon, for example, is renowned for being able to form millions of different compounds, a characteristic that is the foundation of organic chemistry and, by extension, all of life on Earth. Nonmetals are all around us and play integral roles in our daily life. Take oxygen, for instance. It's a nonmetal that's essential for our survival. It's in the air we breathe, the water we drink, and many of the materials we use every day. Another example is nitrogen, which makes up about 78% of our atmosphere and is a crucial component of the proteins in our bodies. Then there's carbon, the backbone of all life as we know it. It's in the food we eat, the clothes we wear, and even in the diamonds used in jewelry. Even the pencil lead you might be using to take notes while watching this video is actually made of graphite, a form of carbon. So, nonmetals might not be as shiny or conductive as metals, but they're just as important, if not more so, in the grand scheme of things. They're the silent workhorses of the elemental world, often overlooked but undeniably essential. With that, we've covered the basics of nonmetals. But how do metals and nonmetals interact with each other? When metals and nonmetals come together, what happens? Well, it's not a dance party, but a fascinating series of chemical reactions that reveal the unique properties of these elements. At the heart of these interactions is the transfer of electrons. Metals, being generous donors, give away their electrons to nonmetals who are more than happy to accept. This exchange forms the basis of what we call ionic bonding. Let's take a real-world example. Picture sodium, a soft, silvery metal, and chlorine, a yellow-green nonmetal gas. On their own, they're not particularly friendly. Sodium reacts violently with water and chlorine is poisonous. But when they meet, they form sodium chloride, or as we know it, table salt. Sodium gives up an electron to chlorine, creating a bond that transforms these two into a tasty addition to your fries. But it's not just about making our food tastier. These reactions have wide-ranging applications. For example, when calcium, a metal, reacts with oxygen, a nonmetal, it forms calcium oxide. This compound is used in making cement and glass, two materials that have quite literally shaped our modern world. And how about the reaction between iron and sulfur? When heated, they form iron sulfide, a compound used in a variety of industries, from agriculture to electronics. These are just a few examples of the incredible chemistry happening when metals and nonmetals interact. Each reaction, each transfer of electrons, gives us new compounds with unique properties that we can utilize in countless ways. But what makes these reactions even more intriguing is what happens after the electron transfer. Metals become positively charged ions or cations, while nonmetals become negatively charged ions or anions. This charge difference is what makes the bond between them so strong, creating compounds that are stable and often quite useful. That's a quick look at how metals and nonmetals interact. But why do metals conduct electricity and nonmetals don't? Well, let's dive into that next. Ever wondered why you can't use a wooden spoon to conduct electricity? It's because the presence of free electrons in a material determines its ability to conduct electricity. Metals, with their unique atomic structure, are packed with these free electrons, making them excellent conductors. Let's delve into the atomic structure of metals to understand this better. Metals have a sea of electrons that are loosely bound and free to move around. Imagine a bustling city during rush hour, with people moving freely, navigating through the streets. That's how electrons behave in metals. Now, when an electric current, which is essentially a flow of electrons, is applied to a metal, these free electrons quickly align themselves and move in the direction of the current. This swift movement and alignment of electrons allow metals to conduct electricity efficiently. On the flip side, nonmetals lack this sea of free electrons. Their electrons are tightly bound to their atoms, leaving no room for free movement. Picture a quiet town where everyone stays indoors, and there's hardly any movement on the streets. That's the scenario in nonmetals. When an electric current is applied, there are no free electrons to align and move in the direction of the current, making nonmetals poor conductors of electricity. Interestingly, this property of metals and nonmetals is utilized in various practical applications. For instance, the wires that light up your home are made of metals like copper or aluminum, chosen for their high electrical conductivity. In contrast, the insulation around these wires is made from non-metallic materials like rubber or plastic to prevent any unwanted flow of electricity. So the next time you switch on a light or plug in a device, remember that it's the unseen movement of free electrons in metals that makes it all possible. And equally, it's the lack of free electrons in nonmetals that keep you safe from electric shocks. And that's why metals conduct electricity and nonmetals don't. So, let's recap what we've learned about metals and nonmetals. We've dived deep into the world of these intriguing elements, discovering that metals are generally shiny, hard, and good conductors of electricity, while nonmetals are usually dull, brittle, and poor conductors. These properties are no accident, but the result of the unique atomic structures of metals and nonmetals. We've also explored how these elements interact. Metals tend to lose electrons and form positive ions, while nonmetals gain electrons and form negative ions. This difference is key to understanding why metals and nonmetals behave the way they do. And let's not forget our discussion on electricity. Metals, with their sea of free electrons, are excellent conductors. Nonmetals, on the other hand, lack these free electrons, making them poor conductors. That's all for today. Remember, science is all around us, even in the smallest atom of a metal or nonmetal. Until next time.